So let's talk about autonomous differential equations, and we're going to sketch the slope fields for these. So an autonomous differential equation is one where we have dy by dt on one side, and then the other side is a function of y, or a function of the dependent variable. And the first slope fields we sketched were of this form. We saw the simple example dy by dt equals, I forget if we did 2y or 3y. The cool things about these is that all slopes are equal along any horizontal line. So if you remember on this one, we sketched on the x-axis, everything was horizontal, and then we had slopes going steeper and steeper as we got bigger, and then going steeper negatively down here. It looked something like this. It's not a perfect sketch. Note that all autonomous equations are separable. So they're easy to solve explicitly. You can just divide both sides by f of y, multiply both sides by dt, and then you've got it separated. You might have to do some funny partial fractions, or it might be difficult to integrate. But as long as it's a function that whose reciprocal can be integrated, you're good. Let's do an example of one that's a little bit more complicated than these linear ones. So let's look at dy by dt is 8 times y squared minus 4 quantity squared times y squared plus 2y. Okay, so they give it to you in this format. Probably the first thing to do is factor, fully factor. So let's see, y squared minus 4 is y minus 2 times y plus 2. And the whole thing was squared, so these are each squared. And then we common factor out a y here. This is a y plus 2. So actually we have 3 y plus 2's. We have 8y times y minus 2 squared times y plus 2 cubed. Okay, and let's just look at what that looks like. I think the easiest thing to do is kind of sketch this polynomial. It's a 6th-degree polynomial, which maybe we don't know how to sketch exactly, but we can kind of approximate. We know where the roots are going to be. The roots will be at 0, 2, and negative 2. 0, 2, negative 2. We'll call this 1, although we don't really care what the scale is on the y-axis. And let's see, this is a single root, this is a double root, and this is a triple root. So what does that mean? The single root looks like it just passes through the origin. The double root at 2 is going to be parabola-ish, pointing up or down, we don't know. And then the triple root at negative 2 will be some sort of cubic. Either, oh, this is terrible, other way around. It goes flat there, but it could go either that way or that way. So we have some sort of sketch of that. And let's just see, as y gets really big, positively, dy by dt, let's just look at this. This also gets really big, right? Positive infinity. So we need to be going up here, so that means we're taking this one. So let's see, we have this, we go up, and then we need a single root at 0, and then we need to come back and do some sort of triple root business. It doesn't really matter if you draw this cubic part accurately, but at least not for the purposes of doing this, because we're only really looking at the signs. So we notice that we got positive slope here, negative slope here, and positive slope here. Okay, now let's see if we can sketch the slope field. So we have t, y, pretend that's on the graph line. Okay, and then we're going to get some colors. So we have slope of 0 at 0, 2, and negative 2. These are now horizontal lines, right? So slope of 0 here, slope of 0 at, we're going to put I'm going to put 2 up here. So every 2 blocks will be 1, negative 2 will be down here. Okay, so that's 2, negative 2, 0. And then what happens? As we go from, let's say, 0 to 2, the slopes are positive, and they're getting bigger, and then they get smaller. So we'll get, I don't know, some slope here. We don't know what it is, but it'll all be the same. And then we'll get steeper, and then less steep again. Something like that. And they'll all be the same across these lines. And so if I try to draw a solution curve in here, I'd be close to horizontal, steeper, getting steeper here, and then getting less steep again. So my solution curves in this area would look like this. And they'd all be parallel. Okay, what about above 2? Well, I'm getting more and more positive. So I'm getting bigger and bigger. So my solution curves here, I start with a small slope, I get steeper and steeper and steeper. So solution curves look like this. And then what about down here? Well, I have a small negative number, maybe here, and then I get a larger negative number. I max out wherever that is, and then I get small again. It's all negative. So that looks a lot like this region. We have small slope, bigger slope, smaller slope, something like that. All the solution curves look like that. And then down here, we are positive again. So small positive number near negative 2, getting bigger as we get down here. So we're getting, this is going towards there, like that. Solution curves are that way. And notice that solutions near negative 2 tend towards negative 2, all of them. All of the curves will tend towards negative 2. So we call this stable equilibrium states. The equilibrium states are 2, 0, negative 2. This is a stable equilibrium. 0 is unstable, meaning if we're right at 0, then yeah, we'll stay at 0 forever. But if we're a little bit off of 0, we're going to go away from it really fast. And then 2 actually have some solutions going towards it, some going away. So we call this semi-stable. For a little bit above 2, we're going to go away from it. For a little bit below 2, we will go towards it. Okay, and then so basically for any polynomial, well, anything that you can sketch a graph of, really, but polynomials are easy because we know the roots, then we can sketch the slope field of an autonomous equation.